Hello everyone, and welcome back to another episode of Math with Mr. Kovo. Today we're going to continue our kindergarten math series, and we're going to be doing derivatives. I'm going to show you guys how to do the derivatives of a few very simple functions. So let's get on to it. Okay, let's get started here. First, we're going to do our function that is a combination of a logarithmic function as well as a rational function right here, with a numerator and a denominator both having an x. Now this is going to make for an interesting derivation. For the log function, as we know, the derivative of log x is 1 over x ln b, b being the base of the log. Now in this log, if there's no base, then it is assumed to be base 10, as we know about logs. So the derivative for this is going to be a simple 1 over ln 10, which is now 2.3 times x. We're not going to simplify this too much, but let's keep moving. Now for this function. The rational function is going to follow the quotient rule. The quotient rule is what happens when you have the form of fg over gx and you want to find the derivative. What you do is you take the denominator, the first function, and you keep it the same. Then you take the top function and you take that derivative, the numerator, and take the derivative of it. And you subtract and go vice versa. Derivative of the denominator, and that room there, and the same part of the numerator. And then all of that is going to be over the denominator function, just the denominator function, not the derivative of it, squared. And you can see that happening here. We fix the bottom function right here, and then we take the derivative of 2x minus 2, which is just 2. Subtract that with the derivative of the bottom function, which is 2x, and then multiply that by this. And that's all over x squared minus 1 squared. Then you simplify it a bit, and I got 2x squared plus 4x minus 2 over x squared minus 1 squared. That is the derivative of this function. Let's go to function 2 now. Now this right here is a composite function, meaning that there is a function inside the other function. As you can see right here, if I were to replace sine x with x, then what would this be? It would be a simple polynomial, right? Instead, I have put a sine x in there in place of x. If you'd like, I can have it as the function of where g of x equals sine x, and then f of x is equal to g of x cubed plus g of x squared, and so on and so forth. That's another valid way to write it, but I just did it directly for convenience. Now, let's get on to deriving this. This is going to follow the chain rule and the derivatives of sine rule. As we know, the derivative of sine x is cosine x multiplied by the derivative of that x value. The value right here is just going to be sine x, so, it's just x, so we're not going to do that, because it'll just be an additional multiplied by 1, and it's already being multiplied by 1, really. This is where a lot of people need to be careful. You see that right there. That 3 means that this 4 sine x is to the power of 3, right? Keep that in mind. Before you start this equation, I recommend writing it out in this form right here, so you can probably see how to take the derivative. As we know with the chain rule, we multiply it and subtract 1, so we get 12 sine x squared. And then we take the derivative of what's inside the bracket, which is going to be cosine x. And then we do the same, we get 2 sine x cosine x, and we get 3 cosine x at the end, and that 2 doesn't have an x on it, so it just gets dropped. Now with this, we can simplify it a little bit by just taking the cosine term out, and then we get a fairly standard looking polynomial, quadratic, 12 sine squared x plus 2 sine x plus 3 cosine x on the outside. And that is the derivative of our second function. Okay, now we're going to take a look at continuity. A function is continuous if over all of its twists and turns, there's always an x value, or there's always a value, like here along the x and the y axis. There are many types of discontinuities. So if you have a piecewise function, oftentimes one you'll see is a jump like this. So this function is moseying along its business, and this one abruptly starts right there. You can have a point discontinuity where there's just a small little dot that is not part of it, and there can be an infinite discontinuity where it goes right to infinity and it is not continuous. So in order to find continuity, you can check the limits, and that's what we're going to do with these two functions right here. So as they're defined on Desmos, if x is greater than 0.0001, then it belongs to the log x plus 2x minus 2 x squared minus 1 function. If it is less than or equal to 0, then it follows the cubic sine function. Something that's interesting is that on Desmos, these two functions look like they're touching. And they look continuous, like they're touching and all would be well. But that is not the case, and this is why it is very tricky, and you need to check it mathematically here. I'll take you guys over a second. So you can see, it looks like those two functions are touching, right? It looks like it. However, those eagle-eye viewers will already see why it isn't. So there is no definition of any function given between 0 and 0.0001. So in that little gap right there, which if you really zoom in, like in zeros of zeros of zeros, there's no function and there will be nothing there. It is also, so there we go. It is not defined as 0,0001. There's no right-hand limit as at x equals 0, and therefore it is not continuous, because again, as you can see, we have the left limit as it's going towards 0, but there's no right-hand limit. After 0 to this point, there's no limit. There's a gap between 0 and this point right here. And vice versa. There's no left-hand limit at x equals 0.0001. Therefore, it's not continuous at this point, not continuous at this point. And then, from this equation right here, x equals 1 is a vertical asymptote. Alright, that's it about continuity. At x equals 0, x equals 0.01, sorry, 001, and x equals 1, it is not continuous. Differentiability. Think about it. A derivative, or differentiability, is when you can find the slope of any function, the slope of the tangent line, right, or the tangent. If a point does not exist, if it's not defined by a function, then you cannot find its tangent line. Therefore, at all these points where it's not continuous, it is not differentiable, and overall, the function is not differentiable and not continuous. Now we are briefly going to talk about the x-intercepts. We're not going to spend too much time on this because we run into quite an issue the moment we try and solve our one function that is going to have x-intercepts when we try and solve this for 0. The other function, the log function, will not have x-intercepts. You can see this graphically, and you know this too because it has a asymptote. As you can see right there, it will have a vertical asymptote and therefore not have any x-intercepts. Okay, now this equation right here is a mess to solve. A cubic function, as we know, can only really solve through synthetic division and a sort of trial and error. And this, you do not get any rational roots. If we were in some more advanced math, we would solve this numerically, but instead we're just going to do it graphically. We're going to look at our graph and derive an equation from it. So we can see that there is an intercept at 0.48, 0. You can see it on the graph. Right there. From there, we can derive our equation. So 0.48 plus the period of sine, which is 2 pi n, where n is equal to any real integer, and then you have the other intercept, 2.66 plus the exact same. There we go. Okay, now we're going to be talking about increasing and decreasing intervals. Simplest way to do this is to take the derivative, set it equal to 0, and find the critical points. Critical points in the same way that you would find x-intercepts. So of course we have the derivative here, and for the simplicity I factored out cosine. We'll get into what cosine is when it equals 0 in a moment, but let's take this term right here. 12 sine squared x plus 2 sine x plus 3. Now, if you were to let sine equal y and try and do this in the quadratic formula, you would not get any real solutions. So thus, this interval of increasing and decreasing is only going to be governed by that cosine. This term right here does not matter. Now, let's make that 2 a bit more obvious. When cosine is equal to 0, it is 90, or in radians, pi over 2. Everything on this side of pi over 2 is increasing, everything on this side is decreasing. But if you have done calculus with advanced functions, you're going to say, hold on for a minute there. Because, as we know, cosine and all the trigonometric functions are cyclical. Their period determines how many of these there are going to be, how many intervals of increase and decrease. Because we know that a cosine wave isn't just that and it stops unless it's restricted. It keeps going on and on and on forever. So thus, you can work out a small equation to see where the intervals of increase are and the intervals of decrease. And it starts with the period, which is 2 pi, times n, where, I should write that, n, r, z. So n is equal to a real number and an integer. I suppose that's implied, but n is any real integer, any whole number, then 2 pi times n minus pi over 2 to 2 pi n plus pi over 2 is going to be the levels of increase. And I have that written out graphically here. So let's say you're starting with 3 pi over 2. Sure, let's use this. If n is 1, so this is n equals 1, you get 3 pi over 2, and then it's going to increase until you get 5 pi over 2. If you want, you can do the simple math there, but it is rather simple. 4 pi over 2 plus pi over 2 is 5 pi over 2, 4 pi over 2 minus pi over 2 is 3 pi over 2. And it works for the decreasing as well. As you can see, this number this value is just put right here, because from this apex, you're going right down. Now, then it just repeats, and for this part, for the decreasing, it is a bit different. It is 2 pi n plus 3 pi over 2, and here's how that works. Again, we're going to say our integer is 1, n is 1, so 4 pi over 2, that's the equivalent, plus 3 pi over 2 equals 7 pi over 2, and that's what I have there, and this has been double checked on Desmos graphically. Okay, now let's do the minimum and maximum with the increasing and decreasing points that we found on the last page. So, in order to find the y value for the minimum and maximum, and remember, it's a sine and cosine, so there's going to be many of them. To find the amplitude, or the y value, what you're going to do is you're just going to plug in whatever x value you got for your maximum and your minimum. So for the maximum, it was pi over 2, we found that. So you're going to plug that in, and interestingly, sine pi over 2 is just 1, which is awfully convenient. So you just get 4 plus 1 plus 3 minus 2, which is going to be 6. You can check that graphically, and it works. So you just sub in your previous equation to account for all the other variations, pi over 2 plus 2 pi n, comma 6. And then for the local minimums, it's the exact same thing. We know that 3 pi over 2 is going to be our x point at the minimums. So we're just going to throw that into the same equation down here. And wouldn't you know, you get almost the exact same thing, except negative 1. Sine 3 pi over 2 is negative 1. So that's going to be negative 4 plus 1 minus 3 minus 2, which is negative 8. And that value is going to go right there. And again, you can check this graphically on Desmos if you'd like, but these are the values you find algebraically that also correspond to the graph. Nice. Right, now let's do concavity. If you don't know, concavity means the way in which the slope is progressing. This can be concave like this, or concave like that, right? If it's positive, it's like this. If it's negative, it's like that. And it is found using the double derivative equaling 0, in the exact same method as finding the critical points. It is used except with the double derivative. So first we have the first derivative right here. Then what we do, we take the second derivative. And as you can see, this right here is going to be a product rule. It's going to be this multiplied by this. So we need to take the derivative of each. So to start, we're going to fix the first term and take the derivative of the second, which is negative sine x. As we know, that's the derivative of cosine. Ran out of room, so I have a plus right there. And then this is the second part. We're going to fix the second term, cosine x, and then take the derivative of this. Now, this is quite a long one. First, you have to apply the chain rule, always. You take the squared right here, multiply it by 12, you get 24 sine x, but you're not done there. Make sure you multiply the x as well. So you add a cosine onto that right there. And then you take the derivative of 2 sine x, which is just 2 cosine x. And that 3 gets cancelled out. You can simplify this to this, where you have the negative sign out front, you take that from the sine x right there, and then you have this term unchanged, sine x plus cosine x squared, because what you'll notice is that this cosine x is going to be distributed onto all of them, which each have a cosine, so you can take cosine x out, and then you're left with 24 sine x plus 2. I suppose you could factor 2 cosine squared x out, but you don't need to, especially because this right here would be a nightmare to solve for 0. This is what we call a transcendental equation, where there's not a numerical value that can be easily attained, and we are not going to bother because there's an easier pattern that is showing itself when you actually look at graph. So this is what I've drawn out right here, and it is exactly what is on Desmos for this graph. The very first point of inflection, let me just draw x and y axis briefly right there, that's the x-axis. The very first point of inflection is the y-intercept at -2, and it starts at 0. And then you follow a very interesting pattern. If you go along that -2, you find that each point of inflection increases by around 3.14 each time. So, there we go. The points of inflection are just pi, n, and that's quite literally it. Alright, and before we go here, the points of inflection would follow this little equation right here, pi n, -2. Because again, as we know, cosine and sine are cyclical. So, you'd have, if n is equal to 0, you just have 0, -2, n is equal to 1, 3.14, -2, or just pi, -2, 2n is 2 pi, and -2, and so on and so forth, and it works the opposite way with negative numbers as well. So negative 1n would be negative pi, comma, -2. That is your points of inflection.